Okay, I'm Jose, and I'm explaining the Mousetrap Spring Car. And we to find the energy stored in the Mousetrap, we use the Torsion wheel from Logger Pro. We got the data from that, and when fully loaded at 180 degrees, the full force was 5.233 newtons. And now for the position and time graph, when we recorded our car and analyzed it using a tracker, this gave us this graph of position and time, and our car went 4.1 meters, and that was the displacement. And then mass of the Mousetrap, for that we use the equation 9.8 newtons equals 1 kilogram, and that's total force over 10 newtons per kilogram, and the total force is equal to 5.233 newtons, and when you divide that, it is 0.5233 kilograms for the car. The maximum velocity was 0.622 meters per second, and you plug that into the equation for kinetic energy, which is 1/2 mv squared, and then it's 1/2 times 0.5233 kilograms times 0.622 squared, and when you multiply that all out, it is equal to 0.101 kilojoules. And again, the displacement was 4.1 meters. There are two different accelerations for the car, because first, for the first few moments of the car, it speeds up. Then afterwards, once it hits a maximum velocity, the car slows down. And the lines are the slopes of the velocities of the car, which are the two different accelerations. The positive acceleration for when the car is reaching its max velocity is 0.06875 meters per second squared. The car's negative acceleration for when the car is decelerating to its zero velocity is negative 0.08406 meters per second squared. And now we have a picture of a force diagram. And when the car is first speeding up, it weighs 5.233 kilograms, and the tension on the car is provided by the string, and it provides 5.233 newtons of force forward. And of course, there is friction pulling it back, and there is no weight or normal force because they cancel out since they equal each other, and the car is not gaining or losing altitude. And then for slowing down, the car no longer has any more tension since the string has released all its energy, so the only force acting upon it is friction. Total force, or net force, is the sum of the forces, which is equal to the mass of the car times the acceleration of the car. To find the sum of the forces for when the car is speeding up, you multiply 0.5233 kilograms, the mass of the car, times 0.06875 meters per second squared, the acceleration of the car, to get 0.036 newtons for when the car is accelerating towards its maximum velocity. To find the sum of the forces for when the car is slowing down, you do 0.5233 kilograms times negative 0.08406 meters over second squared, and that is equal to negative 0.044 newtons. For the energy flow diagram, the car begins at rest with its velocity of 0, and all its energy is in E elastic, so that gets 6 blocks, none for E kinetic since the car is not moving, and none for E gravitational since the car is not moving or up and down. But you take away 1 for E disk since the car loses energy and friction. And then the car in the second picture is at velocity max, and it no longer has any more E elastic since it's all gone, but it has been converted to E kinetic, so that has 5, and there is once again no E gravitational. And in the second energy flow diagram, the car has reached its maximum velocity, so all its energy is in E kinetic, which is 5, and then energy dissipates due to friction, so it loses 5, and it reaches 0 for all energy since the car no longer has any more energy.